Hi guys, this is a mathematics for engineering 3 and this is the last video. Okay, so I know you would be very happy, okay, to go through to the last video. In this video we're going to be looking at the solution of the second order differential equation when the roots differ by an integer. Okay, in the previous clip we looked at the case where r1 and r2 are the difference between r1 and r2 is an integer. It's not an integer, right? It's non-integer. And in this video we're going to be looking at the case where the difference between r1 and r2 are an integer. Okay, and let's look at it how to do it. Okay, so let's begin. So the method, first, we solve, we go through all the same things, right? We checked with, sorry guys, this is 4.3. Okay, so first we have the zero step, which is to check, right, whether or not the point is a regular singular point. Okay, and you know how to check that, right? After that we write down y equals, what is it, summation n from 0 to infinity an x to the n plus r. Okay, and then we go through all the messy process, right? And then we get the indicial equation and the recurrence relation. Okay, after that we solve for r1 and r2. This is exactly what we did in the last video. Okay, but in this video r1 and r2 differ by an integer. For example, r1 is 2 and r2 is 3. So the difference between r2 and r1 is 1, right? Which is an integer. Okay, which is an integer. So we can't use the previous section, which is to let y equals y1 plus y2, right? And y1 is the summation an x to the n plus r1, and y2 is summation bn x to the n plus r2. We can't really do that. We need to do it like this. So first we assume that r1 is bigger than r2. Okay guys, when we solve the initial equation, we get r equals 2 and 3, right? And we don't actually know which one is r1 and which one is r2. It's up to you, right? It depends on you, like if you want to call this r1, if you want to call this r2. So guys, you need to call the bigger one r1. So r1 would be 3 and r2 would be 2 in this case, by the way. So we assume that r1 is bigger than r2. Okay, so r1 is bigger, r2 is the smaller. Okay, and then we substitute r with r2. Okay, we try substitute r with r2, and then if we get all the coefficients a0 a1 a2 until a0 is not 0, is any constant. So the solution is y equals summation n from 0 to infinity an x to the n plus r2. So basically you can just ignore r1. Okay, let me talk about that again. First you get r1 and r2. Okay, you take r2, which is the smaller one, you take the smaller one, and then you try to find the constants a0 a1 a2 a3. And if there aren't any problems, in the process, then you get the solution y equals summation n from 0 to infinity an x to the n plus r2. This one is actually easier than the previous section, because in the previous section you need to have y1 and y2, right? And you do need to use both r1 and r2. But here, if r1 and r2 differ by an integer, you can try using the smaller one called r2, and then you get the solution y equals an x to the n plus r2. Okay, it means that we don't use R1, which is the bigger R, at all. We don't use R1 at all. Okay. But if there's a problem, but that is not going to be in the exam. Okay, that's not examinable. Not examinable. It's not examinable. So, just to conclude here, because we have only one case, it's easier to conclude, okay? So, first you find R1 and R2, okay? And then you take the smaller one. You take the smaller one, so-called R2. And then you find all the coefficients, and the solution is y equals summation n from 0 to infinity, a n x to the n plus R2. That's it. Very easy. Okay, it's actually simple. It's actually simpler than the previous video, the previous section. Okay, let's look at an example. Okay, let's look at an example. For example, this one, x y double prime minus 4 plus x y prime plus 2y. Okay, first we know that b2x is actually x and b2 at 0 is actually 0. It means that x equals 0 is a singular point, okay, which means that you can't use the method that you use to solve an ordinary point. You can't use that, which is section 3. Okay, it's a singular point. And you need to show further that is a regular singular point. So you take px, which is minus 4 plus x divided by x, and qx, which is 2 divided by x, and you look at 1 over x minus x0, which is 1 over x, and you have here the factor, right? The power of the factor 1 over x for px is 1, which is less than or equal 1, and the factor here is 1 as well, which is less than or equal to. So it means that x equals 0. Okay, you should write that down, okay, in the exam. You need to write that down, that the power of 1 over x for the power of the factor 1 over x of px is 1, which is less than or equal 1. Oh, let me write that down, okay? The power of the factor 1 over x of px is 1, which is less than or equal 1, and the power of the factor 1 over x of qx is 1 as well, which is less than or equal to. That means x is a regular singular point. Okay, so right now we know that x is a regular singular point. Right now we can write y as summation n from 0 to infinity a n x to the n plus r. Guys, this is what we have been doing so far. Is exactly the same as in the previous section. After that, we find y prime, which is what is it? Y prime would be summation n from 0 to infinity a n plus r x to the n plus r minus 1. And y double prime would be summation n from 0 to infinity a n plus r minus 1 x to the n plus r minus 2. Okay, then we get y prime, y prime, y double prime. After that, we substitute y prime and y double prime into the differential equation. Okay, so what we have would be x y double prime, right? X y double prime. It means that I need to multiply x here to y double prime. Okay, and I get x to the n plus r minus 2. So that will be n plus r minus 2 times x. That will be n x to the n plus r minus 1. Okay, I'm trying to do it quicker. Okay, so it will be n from 0 to infinity, n plus r, n plus r minus 1, x to the n plus r minus 1. And the second one would be minus, and that would be 4 times y prime and x times y prime, right? So that would be summation n from 0 to infinity, 4 n plus r x to the n plus r minus 1 minus summation n from 0 to infinity and then x times y prime. That would be n plus r x to the n plus r. You get that? This part is actually these two lines. Okay, so I first multiply 4 to y prime, so I get this 4, and this is y prime. Okay, and after that I multiply x to y prime, so I get y prime, but instead of x to the n plus r minus 1, I get x to the n plus r because it multiply x, so n plus r minus 1 plus 1, this is n plus r. And the last one, that would be, guys, I'm trying to do it quickly, okay, shorter, because this is what you should do in the exam. You shouldn't keep writing, so many things. Things that you can do it quick, because as you say, it's a lengthy process. So if you can get it quick, it's gonna be better, okay? So n from 0 to infinity, 2 x to the n plus r equals 0. Okay, good. After that, let me group, okay, the first and the second guy, the third and the fourth guy, they have the same exponents. See, so let me work it out a little bit. Okay, so it will be summation n from 0 to infinity, and then it would be n plus r minus 1 minus 4 n plus r, and then we have x to the n plus r minus 1. You get that? Here n plus r times n plus r minus 1 is this guy, and then 4n plus r is this guys. Okay, and then I pull an x to the n plus r minus 1, x to the n minus r n plus r minus 1 out here. Okay, so I group these two guys together here. Okay, and then the next one would be plus summation n from 0 to infinity, and that will be minus n plus r plus 2, and then we get an x to the n plus r equals 0. Okay, and that would be summation n from 0 to infinity, and here I can pull n plus r out, right? So I would have n plus r, and here I would have n plus r minus 1 minus 4, and here would be an x to the n plus r minus 1, and the other term would be, second, the other term would be plus summation n from 0 to infinity, and then I pull minus can I pull minus 1 here out? So I would change this to minus 1, and here it would be n plus r minus 2, an x to the n plus r equals 0. Okay, guys, if I pull minus 1 here out, I need to change this to minus as well. Okay, because if I push it back, there will be minus n plus r, and this would be plus 2 as expected. Okay, and then let me rearrange the terms a bit. So what I have here would be summation n from 0 to infinity, n plus r, and n plus r minus 1 minus 4, that will be n plus r minus 5, an x to the n plus r minus 1. Okay, x to the n plus r minus 1, and minus summation n from 0 to infinity, and this would be n plus r minus 2 an x to the n plus r equals 0. Okay, so first we just rearrange the terms, right, to make it look prettier. After that, we're gonna change the exponents, x to the n plus r minus 1 and x to the n plus r. So we will somehow change x to the n plus r to x to the n plus r minus 1. So I'm gonna do it a little quicker than what we did. Okay, so here that will be summation n from 0 to infinity, n plus r minus 5, an x to the n plus r minus 1. I'm not gonna take that out and write, separately and then put it in again. Okay, that takes time. Okay, we try to do it quick. So here it will be minus summation. Guys, here this is the place where we need to change. We need to change n plus r to n plus r minus 1, right? So, instead of going from 0 to infinity, we need to go from 1 to infinity. And then we substitute n with n minus 1 plus r. Okay, plus r minus 2. an minus 1 x to the n plus r minus 1 equals 0. Okay, if we change from 0 to infinity to from 1 to infinity, we substitute n with n minus 1. Guys, here it n minus 1 plus r minus 2, right? Can I change it to n plus r minus 3? Okay, I hope that is not too hard for you guys. Okay. After that, the same process, guys. We will split this into two terms, right? The first term will be when n is 0, and the second term will be, the rest. And what we have would be, I substitute n with 0, right? So I get r minus 5 and an x, a0 x to the r minus 1 plus summation n from 1 to infinity, n plus r minus 5 an x to the n plus r minus 1 minus summation n from 1 to infinity, n plus r minus 3 an minus 1 x to the n plus r minus 1 equals 0. Okay, and then this is, guys, don't forget, we have done that many times already. So here is when n is 0. Okay, and the second term is when n is 1 to infinity. So I will just rewrite this again. R minus 5 a0 x to the r minus 1 plus summation n from 1 to infinity. Guys, as you can see, you have the same exponents already. You have the same summation, right? So what I can do is that I can group the two summation together, right? So what I have would be n plus r minus 5 an, okay, minus n plus r minus 3 an minus 1 x to the n plus r minus 1 equals 0. Okay, so what we have, we set all the coefficients equals 0. So what we have would be r minus 5 equals 0. And okay, it should actually times a0 as well, equals 0. And the other one would be n plus r minus 5 an minus n plus r minus 3 an minus 1 equals 0. And we call this equation the recursive range relation. And from here, we get r minus 5 equals 0. And that is an indicial equation. Okay. Good. So right now, we have that our r is 1 and, sorry, is 0 and 5. Okay, guys, so far we haven't done anything new. It's pretty much the same as in the previous video. Okay, it's the same as section 4.2 when the roots differ by non-integer. Okay, but here r is 0 and 1. Okay, so I will take r1 as 5 and r2 as 0. Don't forget, guys, r1 is bigger than r2. Okay, so r1 must be 5, r2 is 0. And r1 minus r2 is 5, which is an integer. Okay, so what should we do if the difference between r1 and r2 is an integer? We use r2. Okay, we pick r2 as 0. Guys, don't forget we use the smaller one. Okay, and we know that the solution y. Okay, we first need to substitute r2 into the recurrence relation. Okay, we substitute r2 with 0, so we have this relation is going to be n minus 5 an minus n minus 3 an minus 1 equals 0. But guys, the difference is here. We're not going to write an equals n minus 3 an minus 1 divided by n minus 5. We're not going to do that because right now we don't know whether or not a0 is not 0. Okay, so we're gonna just let n be 1 and then we see what happens. Okay, guys, in the exam it always works because we only look at one case, which is this case, when it always works. Okay, the other case, this one is not examinable, so you can always follow my step here. Okay, and let n equals 1, n equals 2, n equals 3. This is when r0 and r1 and r2 differ by an integer. Okay, so if n is 1, so we would have a1. Okay, let me write that down. So it will be 1 times minus 4 a1 minus plus minus is plus, right? Let's keep it minus for now. Minus 2 a0 is 0, which means that a1 is actually minus 2 divided by is 1/2 a0. Okay, that's what we get for n equals 1. And then if n equals 2, we would have that 2 times minus 3 an minus 2, that would be minus 1 an minus 1 equals 0. Okay, so we have an would be 1 6 a1. Okay, just oops, sorry, here need to change n to 2, and here there will be 1. So a1 a2, here there will be a2 as well, sorry, and that will be 1 6 1/2 a0, so it's 1/12 a0. Okay, next we'll look at when the case when n is 3. Okay, if n is 3, what we have would be 3 times 3 minus 5, that would be minus 2. A3 minus 0, A0 equals 0. Okay, okay. Minus 0, minus 0, A2, not A0, equals 0. Okay, so we have that A3 is actually 0. Okay, and if n is 4, we would have, what is it, 4 times minus 1, A4 minus minus 1, A3 equals 0. So we have that A4 is actually minus 1/4 A3, but A3 is 0, so A4 is 0 as well. Okay, let's go to A5. What would N5 be? If N is 5, we would get 5 times 0, A5 minus 2, A4 equals 0. But guys, don't forget A4 is 0. Okay, so we have 0, A5 is 0. It means that A5 can be any number but not 0, right? Is any constant. Okay, right, we get the same condition. 0, A5 is 0. It means that A5 can be any constant. Okay, and then we look at A6. When n is 6, what would happen is we would get 6. Okay guys, if we know that A5 can be any constant, right? When we have 6, that will be 6, 1, if A6 minus 6, that will be 3, A5 equals 0. So we have A6 equals 3A5 divided by 6, which is 1/2 A5. Okay, and after that we get n equals 7. So we have 7 to A7 minus 4, A6 equals 0. Okay, and so here what we have would be A7 would be 4A6 divided by 2, 7 times 2, and that would be 2/7 A6. Okay, but A6 is 1/2 A5, so that would be 1/7 A5. Okay, 1/7 A5, that will be A7. Okay, let me look here whether or not I get things right. And A8, if n is 8, we would get what is it, 8 times 3 A8 minus 5 A7 equals 0, which means that A8 is actually 5A7 divided by 8 times 3. Okay, and if A7 is actually 5 divided by 8 times 3 times 1/7 A5. Guys, I'm not gonna be computing this value, okay? So I just, you could just finish here. So n can be, 9, 10, 11, and blah blah blah. So right now we have that our solution y is summation n from 0 to infinity a n x to the n plus r2. Okay, and that will be summation n from 0 to infinity a n x to the n plus, and our r2 is 0. Okay, so it's basically a n x to the n, and that would be a0 x to the 0 plus a1 x to the 1 plus a2 x squared plus a3 x cubed plus blah blah blah. Okay, and our a0 is a0. Okay, a1, what is a1? a1 would be 1/2 a0. Okay, a1 would be 1/2 a0, and a2 would be 1/12 a0, and a3 is actually 0. Okay, and a4 is 0 as well, and then we plus a5, which is a5x to the 5. Okay, plus a6. a6 would be, what is it, 1/2 a5 x to the 5, oh sorry, x to the 6, plus a7, which is 1/7 a 5x to the 7, plus a8, which is 5 times 8 times 3 times 7 a5x to the 8. Okay, and let me write that down more clearly. This is actually a0 1 plus 1/2. Oh shit, sorry, I forgot to write x to the 1, x squared, and x cubed. Okay, so let me put x1 here, x squared here, and the rest would be 0 0 0, right? So that'll be 1/2 x plus 1/12 x squared, and then plus a5, and that would be x to the 5 plus 1/2 x to the 6 plus 1/7 x to the 7 plus 5 8 3 7 x to the 8 plus blah blah blah, and that is the solution. Okay, let me wrap it up. Okay, so first we look at the equation, and then we checked whether or not the x equals 0 is an irregular singular point. Okay, which is what we did here, and after that we find y in terms of a n x to the n plus r, summation n from 0 to infinity, and then we take y prime, y double prime. Okay, after that we do substitution, right? And then we get the indicial equation and recurrence relation. After that we solve for y1 r1 and r2, and in this case they differ by an integer. Okay, so if they differ by an integer, it means that you need to use the smaller one, which is 0. Okay, so I take r2 equals 0, and then I substitute r equals 0 into the recurrence relation. Okay, I substitute it here to the recurrence relation. After that, I try to go from n equals 1 2 3 4 5 6 7 blah blah blah. At some point sum a, right? When n is 1, you get a1 equals a1 1/2 a0. When n is 2, you get this a2. When n is 3, it goes to 0. Okay, when a is 4, it's 0 as well. And at some point you're gonna again you're gonna get this condition, which is 0 a5 equals 0. Okay, and then you take that a5 is not 0, it's any constant, and then you go further. How far should you go? Okay, you should go until you get this condition 0a something equals 0. After that, you go, another three terms further so that you can have, one, two, three, four terms here. At least four terms here. Okay, and you should write a0, a5 is not 0, any constants. Okay, and that's it. Guys, you can try doing this as an exercise. Okay, please try doing it. Okay, this one, uh I don't think you should do. Let me double check. This one is, no, this one is not examinable, so you don't need to do it. Okay, this one as well, not examinable. So you can try doing this exercise. Okay, this acid exercise. I'll send you the solution. Okay, and guys, that's it for the, the case where the two roots differ by an integer. And that's it for mathematics for engineering 3. So uh, good luck for the exam, and if you have any questions, any problems, just let me know. Okay, so bye bye guys.